Well, yesterday I was talking about conduction properties in metals, and we dealt with pure metals and impure metals, how the conduction is affected in pure metals by the scattering from atomic vibrations, and in impure metals we introduced the impurity term. And then we very briefly dealt with how the picture is a little different in semiconductors, where we now have to account not only for electrons in the conduction mechanism, but also things called holes, which are the absence of electrons, or they behave like virtual positively charged particles. And I think that's where we concluded. What I'd like to do today, before I take up the topic of thermal conduction, which is also related here, is to briefly conclude with a couple of things on ionic solids and insulators. And polymers and things like that. In here, we're going to make some very broad generalization. I'm not going to go into great detail here, but I just want to briefly say a different kind of conduction mechanism, which is not like the semiconductors or like the metals. Fundamentally here, conduction is a field-assisted, applied field-assisted diffusion of defects. Okay? Field-assisted diffusion of defects. And in ionic solids, we saw the different kinds of defects that are possible. We've got vacancies, interstitials, we've got the Frenkel kinds of defects, the Schottky kinds of defects, and remember we are talking of charge balances and so on. And what we see here is the presence of these defects allows diffusion. So the atoms can move from one position to an empty space because of the presence of these defects. And because these, they are not atoms anymore in ionic solids, because they are charged species, along with the diffusion of the species, we have charge transport too, which is essentially what we mean by conduction, right? In a normal case, when you're talking of no charge, they are covalently bonded solids or things like that. When the atom moves, there is no charge transfer because they're neutral species. But in ionic solids, along with the diffusion of species, we have charge transport taking place. So it then depends on the density or the concentration of defects that we have in such a material. And the species that could be responsible include vacancies, interstitials, non-stoichiometry, etc. Right? So to take into account all these kind of mechanisms, we will simply put that sigma is equal to the sum of the charge times concentration times mobility for each of the species. Okay, the same equation as before, except now we are summing it over each of the possible types of species. And remember here, Q is not necessarily equal to E. Well, you can't see it right now, but yeah, there we go. Q is not equal to E. Not necessarily. It could be, but it's not necessarily equal to E. Why?
Because the ions might be multiple.
Very good. The charge is not just an electron transfer. There is charged species, ions that are moving, and they may be multiply charged. And so whatever be the charge of the particular ion, 2 plus, 3 plus, whatever it may be, or minus accordingly, will be the value that we have to use in Q. Now, in most of these cases, since it's diffusion, as we said, okay, the key is diffusion. Diffusion is a thermally assisted process. Higher the temperature, faster the diffusion. So we could, in most of these cases, model the behavior of conductivity versus temperature as sigma is equal to sigma naught exponential minus E sigma by kT. Again, a familiar equation, what we call the Arrhenius equation before, which simply we have put E sigma as the activation energy for conductivity. Right? The whole process is diffusion dependent, and so a very similar equation we found for diffusion also, and for vacancy constant. These are all called the Arrhenius equations. And you know then what to do with such an equation, I suppose, to get the activation energy. We plot it and we get the activation energy. There is a special case that comes for thin films. And when I use the term thin films, I'm talking of nanometer dimensions. Okay? We're talking dimensions that are of the order of some nanometers. And in this case, we have to account for another scattering mechanism that is not to be considered in bulk materials. What is that? We're talking of conduction through a very thin film that may be having dimensions something like 10 nanometers or so. And electrons are moving through this. We'll have the usual. There's thermal scattering due to atoms, right? There's impurity scattering, if there are impurities. All that is there. But what else do we need to take into account? I lay the emphasis on the word thin. What is that? Try it. Talk to me. Attraction between? Diffraction. Well, not quite. Okay, scattering from the surfaces. All right. Now you remember, each of these electrons that is moving through is undergoing a random path, right? Getting scattered from different things. Now it has what we call the mean free path or a length in the bulk sample. We said that's the distance it will travel on an average before getting scattered, right? Now what if that mean free path is approximately the same dimension as the thickness of the film? So now the scattering events are taking place not due to individual atoms, but every time it moves that average length, it's hit a surface, either the top surface or the bottom surface. So we have an additional scattering term that is coming in due to the fact that the films are so thin that they are approximately of the order of the mean free path. And in this case, given film thickness we express as d, the mean free path in a bulk sample, okay, that's why the subscript is L subscript B, okay. And when we are talking about thin films, this additional scattering that is coming in, we are talking about d by LB is less than 0.1. This sort of defines the thickness of the film D. It's only about 1/10 that of the mean free path. And typically D has the order of around less than 10 nanometers. Okay? So in such films, we'll see there is an additional scattering term that is introduced, and the resistivity sharply increases. There is you can find plots of resistivity versus thickness, and you find that at very low thicknesses, it sort of increases like that. Because as we come down to the scale of few nanometers, the scattering term starts becoming the predominant factor. If D is even less, we're talking of less than 1 nanometer. 1 nanometer is about 10 angstroms. You're talking of a few atoms, a few lattice constants perhaps. Then we have another problem that conduction itself may not occur because the film becomes possibly discontinuous. Right? It's so thin now that instead of having a continuous film, we have patches, and they don't touch each other. So now the current that is trying to flow here, it's sitting on something. It's passing through this path, but then it can't get here. So when we have very thin films, then we lose conduction altogether. And so what we're talking about with thin films is got to be bigger than 1 nanometer or so that we have continuity in the films. Let me take up the topic of thermal conduction because it is related, at least in the case of metals, to what we're talking about with conduction mechanism by scattering like a free particle. What we see if thermal conductivity, which is really what we will study, is that metals are good electrical conductors, but they are also good thermal conductors. Right? Common experience. You know, wires are used, metals are used to conduct electricity, but we also know when we touch a metal, it feels cold. And the reason it feels cold is because it's a very good thermal conductor. That's the property of a metal. And so we may surmise, knowing that the conduction mechanism in electrical conduction is due to electrons, that these same large body of free-floating electrons may have a role to play in the thermal conduction too. It's a guess that we're making. And that's just a guess kind of thing. But when we look at it, actually the mechanism for metals, it turns out, all the energy for heat transfer is taking place primarily by means of electron transport. The electrons are the carriers of energy, and we'll see how that happens. In the case of nonmetals, we will have a different picture. Why? For thermal conduction. Very good. There are hardly any free electrons there. Most of the nonmetals are insulators. Not all, but most of them are insulators. And by nature of that definition, there are very few free electrons to conduct the heat, if heat is indeed being conducted by electrons. But obviously, even nonmetals conduct heat. There are many good conductors that are non-metallic. So there must be some other mechanism in addition to thermal conduction through electrons that must be operative there. And we will see that in this case, it is through atomic vibrations. The energy is coupled through atomic vibrations and transmitted down the non-metallic material. So phonons are the basic reason for conduction or the mechanism for conduction. Electrons in metals and primarily a phonon-based mechanism in nonmetals. We can consider the case of a metal, and we have heat here. And the question is asked to look at the mechanism a little more in detail. I supplied heat here. How is the heat getting to this end? Right? I'm limiting my heat supply only to one end. What is the mechanism that actually transfers the heat from this end to this end? Broadly, we said it is electrons. Let's look at that a little more. At this end here, the hot end, the amplitude of vibrations of the atom increases. Right? It goes up. As more energy is given, the atoms are vibrating and their amplitudes are increasing as more and more energy is given to it. Which means now that the electrons, in addition to that also, the average kinetic energy of the electron is also increasing. They are also gaining energy from these vibrations by interaction with these vibrations. So what happens to the electron when it has higher kinetic energy? The random vibrations that it is undergoing, the random sort of motion that it is undergoing, it goes through the crystal scattering, that becomes far more enhanced. Okay? So the electron motion is enhanced because of the gain. They move faster, essentially, because they've got higher kinetic energy. Okay? So they gained energy in interacting with the vibrating atoms. Now they are moving faster through the material. And in that process, as they move from one end to the other, they are able to move from the hot end to the cold end, transferring the energy now back there through interaction with atoms. So here, they gain the energy at this end by interacting with large amplitude vibrations. Here, the atoms are not vibrating with such large motion. But the electron now has got higher kinetic energy and can move in this direction. And when it does that, it will take the energy with it. And then back again here, they collide with atoms and transfer the energy. So it is this electron that is taking the energy of the vibration of the atom from this end, the hot end, to the cold end as it travels through here. The term that we used earlier, thermal conductivity, measures how easily heat can pass through this material for a given temperature gradient. So we'll come to some definition, a little more quantitative numbers. Basically a measure of how easily heat or thermal energy is transferred through the material. And we'll continuously see the parallels with electrical conduction. Okay? Thermal conductivity, which we'll define mathematically in a second, is the measure of how easily heat is going to flow from one end to the other. Much like in the case of electricity, the conductivity is a measure of how easily current is going to flow or charge is going to flow from one end to the other. Yes?
So the electron which has given the heat and the other end, you're going to come back again?
Not necessarily. Yeah, there will be a flow, but it is not driven by, it's random, mind you. So there is no net transfer of charge taking place. If I cool it down back again, it will come back here. Okay? We will come to where if we are continuing to provide heat, we will generate a difference in voltage, the thermoelectric effect. So if I heat it long enough and maintain that, yes, there will be enough of a EMF that is going to develop. So that if I don't cool this end down, yes, if I cool this end down, now it's again reverse. So till it comes back to equilibrium, things will flow around and readjust. But if I keep on supplying heat, yes, we will eventually develop a EMF, which is what we make use of actually in thermoelectric effect. The electrons that are able to flow in response to the temperature gradient to produce an EMF. Thermoelectric coolers, all kinds of things, thermoelectric heaters work on that principle fundamentally. They convert the thermal energy to electrical energy. We generate the EMF by means of this transfer. But if I stop heating this end, eventually everything comes back to equilibrium. Okay? All right, here's what the scenario we have. We will look at a cross-sectional area A through which heat is transferred. And we'll look at a thin section of this of thickness, say, delta x. So the area through which it is flowing is A, thickness is delta x. And across this delta x, we have a temperature gradient delta T. One end is hot and the other end is cold. And the heat transfer is from here to here as a result. We define then Q dash as the rate at which heat is flowing from hot end to cold end. Sorry, at which heat is flowing from hot end to cold end. Okay. Q dash is also written as dq by dt. It's a rate. Okay. And two things we can surmise is one, that it will be proportional to the area. Right? The larger the area, we would expect more heat to flow. And the other thing is what? What would it be proportional to? The temperature gradient, right? What is the difference in temperature between that? So that would be defined as delta T by delta X. And therefore we will write Q dash, the proportionality constant being a thermal conductivity okay, times A times delta T by delta X. So we saw the proportionalities, the proportionality constant being the thermal conductivity K. The negative sign here is simply implying what? Towards the colder end, right? That's what the negative sign, heat flow is towards the colder end. And this thermal conductivity term then, K, is material dependent. So for different materials, we have different. So for the same setup, same area, same temperature gradient, we will get different heat flow depending on the values of K. And we'll see that in metals, K is pretty high. But there are non-metals also. We'll see why, for example, diamond, which has got a very high thermal conductivity, though it is completely insulating. Okay? This equation that we have here is also known as Fourier's law. And this is the fundamental definition of thermal conductivity. Q dash is equal to minus K A delta T by delta X is also known as Fourier's law. Now, as I said, there's an analogy with my electrical conduction. So let me write Ohm's law right here. The variation that we looked at was J is equal to sigma E. Let me caution you, sometimes I'm not consistent with my symbols. Maybe I have used the other symbol for E there. And when in books and all, they've got so many types of fonts they can use. I don't have that privilege because I can't remain consistent. So I will at least mention what that term is. So if I am inconsistent, please make sure that you note down what that term means. So here it's a field, conductivity, and current density. All right? I can rewrite this equation, Ohm's law, in a different way. And that would be I is equal to sigma. So J, I'm going to write it as I by A. So I take the A term there, right? And then the field, I can write it as delta V by delta X. And so you immediately see the parallel between these two. I got the area terms here. I got some kind of a gradient over here. In this case, it's a temperature gradient. In this case, it's a volt potential gradient. And then we have some constant term. In this case, it is conductivity, electrical conductivity. In the previous case, it was thermal conductivity. So in essence, both these laws are just the same idea that is being expressed. In one case, we are talking of the transfer of charge across a potential gradient. In the other case, we are talking of the transfer of heat or thermal energy across a temperature gradient. And so we see the two terms, sigma, which is the electrical conductivity, and K, or kappa, I think it should be. It's a Greek term, not the English K, is thermal conductivity. One may guess that these two are related to each other, because essentially it's the same mechanism that is driving both these phenomena. And it turns out that we have a relationship between sigma and this kappa term. It's known by a large name, Wiedemann, I hope I spell it right, yep, Franz Lorentz law, which we will conveniently abbreviate as the WFL law. I'm not going to go on using that word. Three people were involved in finally formulating this idea. Two of them suggested some relationship, and then another guy showed the temperature dependence. And incidentally, this Lorentz is not the same guy as your Lorentz spelled with a T. So they all get us into trouble, because that guy worked with charges and magnets and things like that, right? This guy is a different fellow altogether, but his name also appears for us. And what does this law state? The relationship between thermal conductivity and electrical conductivity is given by kappa by sigma T is equal to CWFL. What is CWFL? It's the constant which is known as Lorentz number, or alternatively as the Wiedemann-Franz Lorentz coefficient. Okay? Kappa by sigma t is equal to C WFL. And what is C? We can have an equation for that. Pi squared k squared by 3e squared. Pi squared k squared by 3e squared, where k in this case is the Boltzmann constant, not to be confused with the kappa that we are using for thermal conductivity. Since these are all constants, k Boltzmann's constant, E and some terms, we can write a number for it, a value for this. 2.44 into 10 raised to the power minus 8 watts ohms per Kelvin square. 2.44 into 10 raised to the power minus 8 watts ohms per Kelvin squared. Okay? That's a constant. You may wonder how they got that. You can do that from experiment, and I'm coming to that in a second. So you can take, we're talking primarily about metals. So what they did is you can take the conduction and plot it for pure metals. What? The thermal conductivity, kappa, versus electrical conductivity, sigma, which are both measurable quantities. So if you take this, what will we expect? For pure metals, what will the graph look like? A straight line, right? Whose slope then is given by CWFL by, CWFL times T. So when they did this, that kappa, which has got units, the conductivity incidentally of watts per Kelvin per meter, that's the units of thermal conductivity, and of course your electrical conductivity per ohm per meter. When they plotted the data, it looks somewhat like this, and then when you model it, you get a straight line. And from such a line, you can then calculate what is this constant. That's how that previous number we got was possibly obtained. It turns out to match this value. So theory and experiment more or less match for us. Now when you look at the equation, the WFL law, we saw earlier that sigma has a 1 by T dependence, right? As temperature increases, conductivity decreases. So what can we then say based on this law about the temperature dependence of thermal conductivity? Given that this is the relationship between thermal conductivity and electrical conductivity, we know electrical conductivity is proportional to 1 by T. So what should be the temperature dependence of kappa? What is that? Go ahead, talk. It is also proportional to 1 by T. It doesn't vary with temperature, according to this equation. Do you see how that works out? All right. Let's look at that. K or kappa, sigma I'm substituting is some constant times, let's call that sigma is equal to B by T, roughly. So B by T, and I've got another T term here. And this whole thing is equal to my constant. It simply suggests that kappa does not depend on temperature, which is strictly not true. Okay? But at least what we can surmise from here is that kappa, or the thermal conductivity, has a weak dependence, if anything, on temperature. And then when we look at experiments, say we take materials, pure metals like copper or aluminum, and we plot kappa versus T in Kelvin. And what we observe is a shape something like this. that it's not strictly true that it's constant everywhere, but above about 100 Kelvin in these cases, we find that the thermal conductivity is more or less constant. Okay? It is related to the fact that the motion of the electrons, the velocity we saw earlier has only got, the velocity u has got only a weak temperature dependence. Right? In an earlier lecture we had seen that. So since the energy is being transferred primarily by the motion of the electrons, and the electron motion itself has got only a weak temperature dependence, therefore the conductivity too has a weak temperature dependence. In the case of nonmetals, we said that the conduction mechanism is not by electron flow, but rather by phonon mechanism, or lattice vibrations, or atomic vibrations. We can simplify our picture by looking at the crystal as a series of balls that are coupled together by springs. Right? It's a simplification. But all these atoms are undergoing simple harmonic motion as they vibrate. And this is, say, the case in equilibrium. Okay? They are sitting in equilibrium, and the springs are modeling what? If the ball is the atom, what does the spring model for us in this picture? Bonds. Very good. So what we're talking of is atoms, just modeled more or less by these balls, and springs that model the bonds. Okay? That's the picture we have in equilibrium. Now what I'm going to do is to give some energy to it. So this whole setup in equilibrium has got some average kinetic energy. It's sitting at a certain temperature where all these have some average kinetic energy. I'm going to disturb the equilibrium by supplying heat at one end. And what I have now is that the atoms here vibrate with large amplitudes. Okay? And because these are coupled with each other, I will get an effect that is passed down. You can see the vibrational amplitude is decreasing, but eventually it's getting to this end too. So this is the hot end, and this is the cold end. And in this case, the electron is not taking my heat from one end to the other. It is the fact that these atoms are all coupled to each other, and so the vibration that starts from this end with a large amplitude is getting transmitted by what might be thought of as a vibrational wave. Okay? It's as if we have tied one end of a string, and I'm taking the other end and shaking it violently. Eventually that wave propagates down to the end of the string, the other end of the string that I'm not shaking. And so it's something like that, that this end here, the atoms are getting hot, they're going to vibrate, and then they'll, because they're coupled here, they'll pass on that vibration, and so some kind of a wave of energy is transmitted down here. All right? It is, this part we remember, if you looked at the potential energy versus distance diagram from long back, as we increase the energy, the amplitude of vibration is increasing. So basically this end here, they are sitting at a higher energy, and so they are vibrating with larger amplitudes, and then as we get to this end here, the amplitudes are smaller, but eventually they're all going to get to equilibrium. Now if this is the model, the question may be asked, what would the efficiency, what are the possible factors on which the efficiency of heat transfer would depend upon? Obviously electrons are not playing a role here directly. So if the energy is being transferred in this kind of a wave, what would be some of the factors that could affect heat transfer in a non-metal?
Nature of the bonds.
Nature of the bonds, very good. So one of the factors would be nature of bonds. And more specifically, how strongly these bonds are coupled with each other. The atoms are coupled. Okay? Any other factors? Remember, it's a wave that is propagating. What else could happen in a real crystal to a wave that is propagating? Coordination number. Why would that be important?
Suppose we are having an atom which has the energy and it is surrounded by 8 particles, and the other atom which has the same amount of energy is surrounded by 4 particles. The amount of energy given to, if we assume that
It's distributing it equally.
equally,
Okay, that's a possibility. Coordination number, but I'm not sure that that is distinctly the case, whether it will distribute it equally.
The defects or conclusions,
Why? Why would that be important?
because it would change the nature of the bond.
the vibration will check.
Right? All of a sudden, 1, 2 atoms are missing here. If you simply think of in a one-dimensional linear chain, the wave can't get to this end. Right? So we can put that in a brief form as the scattering of these waves by various mechanisms. So by imperfections of various kinds. Another important thing could be that these waves interact with each other. Remember, there's so many atoms that are vibrating. So the interaction of the vibrational waves with other vibrational waves could also play a role in how the wave is propagating throughout. Okay? And among all these, probably the most critical one is the first one, the nature of the bond. How strongly it is bonded. And it turns out that diamond, which I told you earlier, has a very good thermal conductivity. Now you may be able to guess why it has. Diamond, we know, is a very strong covalently bonded material. Okay? So the coupling is very strong. And if indeed the mechanism of heat transfer is by transfer through these vibrations, we would expect that diamond will have a high thermal conductivity. And it turns out to have a value something of the order of like 1,000 watts per meter per Kelvin. So diamond is a very good heat sink. And people are talking of using it in electronics, not for its purpose necessarily as a semiconductor, which we said a wide band gap semiconductor, or for insulating purposes, but simply as a heat sink. Because as we compress more and more circuits onto the chip, then heat is generated. And if you have a layer of diamond under there on which we can grow things, then it's a very good heat sink. Or if the diamond itself could be used as part of the circuitry, that would also offer advantages. The complementary example of the opposite case are many polymers. Now we know in polymers, the bonding between the chains is weak. If you know anything about polymers, the plastics kind of materials, they're long chain molecules. And between the chains, they are rather weakly bonded. And so many polymers end up with very low thermal conductivities, less than 1 watt per meter per Kelvin. So they make very good thermal insulators. We can define something called a thermal resistance in analogy with electrical resistance too. Okay? We will define for a cube of material, or a block of material, it doesn't have to be a cube, of length L, that heat is flowing in from this end and coming out this side. Then as before, the temperature gradient is delta T. I'm sorry, the temperature different is delta T, the gradient being given by delta T by L. So here we have Q dash is equal to A kappa delta T by L, which we can rewrite as delta T by L by kappa A. Right? I'm just rewriting this equation here for us. And similarly, putting Ohm's law down there for us, I is equal to delta V by R. V is equal to IR, the familiar form. R itself is what? Rho L by A, which I can write it as L by sigma A. So here I can write it then as delta V by L by sigma A. So this term here and this term here are analogous to each other. This is an electrical resistance, R. This is the thermal resistance. Do you see the similarity between the two? And so we define thermal resistance and we call it theta as L by Ka. So in other words, my Q dash is equal to delta T by theta. And we can do something similar to an electrical circuit and draw a thermal circuit. Heat is flowing in from here. The circuit has a resistance theta, thermal resistance theta, temperature gradient delta T, and the heat flow through the system is Q dash. So Q dash is equal to delta T by theta representation. Just the same as we talk for an electrical circuit. I want to go back a little bit to complete a thought that I didn't take up earlier. When we talked about resistivity and things like that, one of the rules I gave you was Matheson's rule, right? Different components of resistivity simply add up. It's a sum. Well, what if you have got more than one kind of material, alloys, mixtures? In those kind of cases, there are some other rules that are useful, and I want to give that so that we can make use of it subsequently. One of the rules that we will make use of is called Nordheim's rule for alloys. And this is useful when we have, for example, an alloy with one element dissolved in another matrix. And the rule simply states that the impurity component of resistivity, mind you, there's more than one, so the impurity component of resistivity is given by C x 1 minus x, where C is known as Nordheim coefficient, and basically it's a measure of how effective is that solute atom that is dissolved in the other matrix in increasing the resistance or the resistivity of that matrix. Okay, so that's a constant, different for different elements. So if you have element A dissolved in B, this constant is different than if B is dissolved in A. Okay, so it depends on what is in larger concentration, which one we call the matrix and which one we call the impurity. X is the atomic fraction of the impurity. All right. So here we can have rho I is equal to C. Now the total resistivity then is rho matrix plus C x 1 minus x. The matrix itself, in the absence of this impurity, has got a certain resistivity, and what this Nordheim said is that part of it is the additional term that is added on to the matrix. The matrix itself consists of the temperature dependent phonon scattering plus impurity scattering term for the matrix itself. There may be other defects and so on that add up here. And then you've got, or not impurity, sorry, what we call the residual scattering earlier. And then you have this term that is being added on by the deliberate alloying. You can see an example, say for copper nickel alloys. If we plot the resistivity versus concentration, one end here we have 100% copper, the other end we have 100% nickel, and it's increasing atomic fraction of nickel, somewhat like a phase diagram, but we are plotting it as the resistivity. It looks something like this. The resistivity goes on increasing as we put in more and more nickel, and then there's a maximum, and then the resistivity decreases. How do we explain this? Here it is pure copper, right? And as we introduce impurities, it is getting more and more resistive because of this coefficient. But this end of it is pure nickel. So again, this term is becoming lower and lower as we proceed in this direction. So in an alloy like this, where we have the complete solubility of one in the other, we get a shape something of this nature. Okay. One important limitation here to remember is we are assuming, for example, in this case, that the valency of what we are dissolving in is the same. There is no additional electrons coming in. But if we use a different valency like zinc or something like that, say in brass, copper zinc alloys, zinc is contributing more electrons than one electron there, and so the conduction mechanism, the term is different. So Nordheim's rule gives us some approximate idea without it necessarily being the perfect value that we can expect for a alloy of this kind. Yes, there was a question here. It's okay? I'll quickly give you a couple of what are called mixture rules, and we'll stop with that. Suppose we have a layered structure. Okay, there's an alpha phase. This is an idealization, and then there's a beta phase. And current is flowing. We can define it either flowing perpendicular to these layers or parallel to these layers. Let's take the case where the current flow is perpendicular to these layers. So in other words, these layers are now in series to the current flow. Current has to flow through this in this fashion. And we can define then an effective resistance, R effective is equal to L rho effective, an effective resistivity divided by A, where A is the cross-sectional area of this setup. And therefore, we will write R effective in terms of its components as L subscript alpha rho subscript alpha by A plus L subscript beta rho beta by A, where L alpha and L beta are the total lengths. In this case, that refers to the thickness, right? Each of these has got certain length. We add up for each phase. So L alpha and L beta are the total lengths of each phase. And correspondingly then L alpha plus L beta is equal to the total length of this, right? So from here, we can then derive an equation. We define chi alpha and chi beta, chi is the Greek terms there, as the volume fractions of A and of alpha and beta. And because the areas are constant and so on, we will then be able to write chi alpha is equal to L alpha by L, chi beta is equal to L beta by L, simply by virtue of the fact that they're all, we are considering an ideal structure with equal areas. Okay? So then we can express the earlier relationship, rho effective is equal to chi alpha, rho alpha, plus chi beta, rho beta. So if current flow is perpendicular through these layers, we will express it in these terms. And this is known as the series rule of mixtures. A good approximation when both the phases have similar resistivities. If one is very different from the other, we can't use it. But if they're similar, this is a very good approximation for a random mixture. Even though we've taken an ideal sort of slabs and layers, this is a good approximation for a random mixture. And if you take then that the current is parallel to the layers, I don't have time to go into it, we will get another expression. That is, now I've applied my current parallel to the layers. And using a similar approach, we can get then sigma effective is equal to chi alpha sigma alpha plus chi beta sigma beta. Okay? And this is then known as the parallel rule of mixtures, where the conductivities for each phase are given in the effective case. There's one more thing I don't know if I have time to do it, probably I'll take it up next time. Let's say when it is all random, one phase resistivity is very, very different from that of the other. Maybe there are a couple of rules. I don't think we need to go into it, but I might just give it to you anyway as a note or something like that, because I want to start another topic maybe from tomorrow. So we'll stop with that here. Maybe I'll just give you a small note which includes two equations. They are empirical relationships that are useful in problems. If, say, air is dispersed inside a continuous matrix pores, how will we calculate the total resistivity? They are not layered structures like this, and the resistivities are very different. So I'll probably just give you a note which includes these two equations. That's all there is to it. Okay? Well, we'll stop with that here.